Hello, class. So since the exam is going to start on Wednesday, right, so it's going to run Wednesday, Thursday, and Friday, like exam 2 did. I'll be doing the review videos so that you can watch them on Tuesday, right, so the day before the exam starts instead of on Wednesday. So today we're going to go over the study guide as we usually do for the exam reviews, and then anything that I notice or that I think is important for you to remember, I'll go ahead and talk about it. Now, as a reminder, in this study guide, you get a couple of things, right? You get the topics we're going to be talking about, and then you get examples from the text, right? Um, any problem you get is going to be a problem that looks like some of these examples. So, for example, if you get a question for 3.11, it's going to look like something similar to a problem in the book from problems 5 to 39 in that section. Right? So, if you want a lot of extra practice, you can definitely look over these examples, right, for each section. As a reminder, the book, if you go towards the end, so the end of the book, there's a part that has solutions for the odd number problems. So if you do practice these problems, I recommend doing the odd ones, right? So you can check your solutions. Also, as a reminder, you get this formula sheet, as you get derivatives of the trig functions, which are usually the hard ones to remember, the derivative of the natural log, log base b, and the chain rule. Right? So those are usually the hard ones. You still have to remember the derivative of cosine and sine. You still have to remember the derivative of the exponential, right? Any base, whether it's base e or base b, right? Whatever b is. So just those are like the quick reminders. Other than that, we can go ahead and just jump right into the topics. Right? So the first thing is section 3.11. Right? So that was related rates. So we did a couple examples in the videos. You can definitely go back to look at those. However, the problem in the, so these are, I also have here the problems from the spring 2019 exam. So these problems are actually good because this one I can use just to represent or to show you all the things you should be careful about, because it's basically the same 3 steps for everything. Right? So when we're going over these related rates problems, I said there are 3 things you basically want to do. The first thing is you want to draw a picture, right? Always draw a picture. It's going to make things easier. And in drawing a picture, you want to label everything, all the variables that you're going to be using, label them in the picture. So that was the first thing, always draw a picture. The second thing you wanted to do was find the rates or derivatives you're given, and then find the rates that you're supposed to find. So find or identify, so right like that. So I identify derivatives given, and the derivative you need to find. So here is going to be useful for you to remember that derivative means instantaneous velocity, or if they just say velocity, you just assume it's instantaneous. So whenever you see the word velocity and it doesn't say average, that's derivative. Rate of change, that's derivative. Slope of the tangent line, that's derivative. Right, so it's going to be useful for you to know that all those things are the same thing. And then the last thing, I don't know if this is how I wrote it in the notes, but you basically want to write an equation that relates to variables. Right. So in this case, if we were going through these steps, so what does the problem say? So air is pumped into a spherical balloon at a rate of 20 cubic centimeters per second. Right? How fast is the radius of the balloon increasing at the instant when its radius is 50 centimeters? So if we first draw a picture, it's a sphere, but I'm just going to draw it, like a circle. But think of it as a sphere. It's in 3 space, so maybe I can do something like this. Right, so it's a sphere. What do we have? It's expanding, or air is being pumped into a balloon at a rate of 20 cubic centimeters per second. So the volume is changing at that speed, right, or at that rate. Right, so it's expanding. At what rate is it expanding? Well, we're given that dv dt. Right, so this is step 1. There's drew a picture. Of course, there are some things we're going to have to identify. Like there's obviously a radius here. So maybe let me just write that first. Right, so there's a radius. So 2, what are we given? Well, we're definitely given dV dt, right? Because we're pumping air at a rate of 20 cubic centimeters. When you see cubic, you want to think volume, right? The unit for volume is cube. Okay? So we're given dV dt here. This is 20 centimeters per second, and centimeters cubed, sorry, per second. What are we trying to find? Well, they're asking for the dr dt. So what is the rate of change of the radius? So dr dt. And here I'm going to use notation 1 over in class. Want to find dr dt, evaluate it, which if you remember, you usually have to evaluate at some point. So you want to evaluate when the radius is 50 centimeters. So evaluate when r equals 50 centimeters. Once you have that, you basically have everything you need, because you're given this equation here. So this is the equation that's going to relate the variables. So this was actually part of 2. Sorry. So 2. And then for 3, let's do it here. You want an equation that relates all of the variables. Well, that's given, right? The volume of a sphere. Now, the only last thing that you want to remember here, and I did this in all of my videos about related rate, is that since the radius is changing with respect to time, it's reasonable to assume that the radius is a function of time. So remember, when you take derivatives here, you want to use implicit differentiation. So for me, whenever I want to remember implicit differentiation, I like to write this out. So since r changes with respect to time, then you may assume that r is a function of t. And I write it this way so that we remember to take the derivative with respect to time. When we do that, we have to use implicit differentiation. Now, of course, the same is for volume. Right? Volume is also a function of time because it's changing with time. Now, once you have all this, you just basically take derivatives of your equation. Right? So this was pi, wait, what was the equation? So the equation was 4/3 pi r cubed. Take the derivative of both sides with respect to t. Right? So take dv dt of both, d dt of both sides. So d dt of v equals d dt of 4/3 pi r cubed. Let's take the derivative of both sides. Here's where you have to remember to use implicit differentiation, right? So the derivative of v with respect to t is just dv dt. So there's nothing crazy going on there. Here we can move the 4/3 out, as well as the pi. Those are constants. So it's the derivative of r cubed. This is a function of time, right? So what's the trick, or what's the shortcut to find the derivative of r cubed, where r is a function of time? Is take the derivative with respect to r and multiply by dr dt. Right. So that was the shortcut. Take the derivative with respect to r, multiply by dr dt. I'm just going to write as r prime. So we get 3r squared, r prime, and then just plug in all the information. You're given dv dt, you're given r prime, and solve for r. Sorry, and you're given r, and you want to solve for r prime. Okay. So this is you can do the rest. This is as far as I'm going to go. So the point of me doing this is for you to remember, if you draw a picture, write down the information you're given and what you're going to find, and write down the equation that relates to variables. If you do all that before you attempt the problem, then you basically have everything you need. You can just, once you attempt the problem, you can just go ahead and take the derivative of both sides of your equation, and you already have all the information written down. And again, this extra step that I always do, remember, so that I remember that I have to use implicit differentiation. I just remember, okay, my variables are changing with respect to time, so they're functions of time. And then when I take the derivative with respect to time, I remember to use the implicit differentiation, which is basically this shortcut. Now, again, we did a bunch of examples of this in section 3.11. I think I did 4 of them, or 3. They all follow the same format, so you can go back and look over them. So the next topic, section 4.11. So here is when we're talking about all this information we can get from derivatives. So for example, we define critical points and inflection points. Right? So what was the critical point? So as you remember, and this is important because it's something that we forgot sometimes, that critical points are not only places where the derivative equals 0, but also where the derivative doesn't exist. Let's say our values where the derivative equals 0, this we did a good job remembering. But the other thing we have to remember is we also include places where the derivative doesn't exist. So, for example, if they were telling us to find the critical points of f of x equals, just do something simple, something like x squared minus 1 divided by x, yeah, something like that. Want to find the critical points, right? So first we find the derivative. So we can use the quotient rule. You can, yeah, so let's just use the quotient rule. So take the derivative of the top, that's 2x, times the derivative of the, times the bottom, sorry, not derivative, times the bottom, minus the derivative of the bottom, which is 1, times the top. Okay, so that's the top part, and then you square the bottom. Now we can simplify this, get 2x squared minus x squared minus minus 1. So 2x squared minus x squared, that's just 1x squared, minus minus 1 is plus 1. Um, so actually, maybe let's change this to a 1, so we have a 1 here. And then it's going to be a minus 1. Because if we have x squared minus 1 plus 1, we don't have any zeros. Okay, so I'm going to change it to a plus there. So this is a minus. And here we have all over x squared. So this is the derivative. Now, what are the critical points? Well, we have to see two things. Right? We first find places where this is equal to 0. So when is f prime of x equal to x squared minus 1 over x squared equal to 0? Well, whenever we have a quotient of functions, that's just the same thing as saying when is the numerator equal to 0. So always remember that. It's a good shortcut. Have a fraction equal to 0, just set the numerator equal to 0. Okay, so this happens when x equals 1 or when x equals minus 1. Okay? So those are two critical points. Okay? But now remember, by the definition, we also need to check places where the derivative doesn't exist. Those are also critical points. So where does the derivative not exist? So notice that f prime of x won't exist when the denominator equals 0. Right? That's the only thing that will prevent this function from existing. Right? Just to look at the domain. Oh, I'm dividing by 0. I can't have that. So this won't exist when the denominator equals 0. So that means we get another critical point. So in this case, what are all our critical points? So CP, or critical points, are, well, x equals 1, x equals minus 1, and x equals 0. So don't forget to include the critical point where the derivative doesn't exist. You always have to check for that. Now, the other thing I wanted to say about critical points is that critical points are inside the interval, right? So if you have a critical point happening at the endpoint of an interval, right? So suppose we have f prime of x equals 0 on, or when, so let's say when x equals 1 and x equals 2, and the interval we're working on the interval, let's say 1 to 3, then out of these two places where the derivative equals 0, only x equals 2 is a critical point because it's inside the interval. So endpoints are not critical points. Right? So implies x equals 2 is a critical point. Right? And then to note here, x equals 1 isn't because it's an endpoint of the interval. So endpoints are not critical points. It isn't because it is an endpoint. So in the exam, if you come up with this situation, I would write this every time. Say, okay, x equals 2 is a critical point, x equals 1 isn't because it is an endpoint of an interval. Okay. So also other than that, I think we did pretty well in terms of finding critical points. It was just remembering that you have to remember that where the derivative does not exist is also a critical point. So in this example, it was x equals 0, right? So we included that as a critical point. And also that endpoints are not critical points. So 2 things to remember. Now going back to this, intervals on which f of x is increasing, intervals when f of x is decreasing. Remember, this was pretty straightforward. Right? Intervals where f of x is increasing is the same as intervals where the derivative is greater than 0. Intervals where f of x is decreasing is places where the derivative is less than 0. So increasing, derivative is greater than 0. Decreasing, derivative is less than 0. Okay. And then one thing to remember here when we're doing these intervals, so we can actually do this example here. So working with the same problems, so determine the intervals in which f is increasing or decreasing, and f is going to be the same function we did in the previous example. So f of x was x squared plus 1 over x. And the interval, we're going to say, so I didn't write it in the previous example, but if I don't write an interval, it means all real numbers, right? So the interval is all real numbers. So when you do something like this, as I mentioned, it's a question of where the derivative is positive or where the derivative is negative. So what was the process to do something like this? If you remember from the first homework, when we were reviewing stuff about just basic algebra, whenever you're interested on intervals, so here basically want to find intervals where a function is positive or negative. And here f prime could be anything. You could change f prime with f double prime whenever, no matter what the function is. Whenever you're trying to find the intervals where a function is positive or negative, what you do is, the first thing, you find the x values, which we already did, find x values where the function, in this case the derivative, equals 0 or doesn't exist. So shorthand, since the function is f prime, basically just find the critical points. Second, you divide the number line using these values. And then divide the number line using these values. Right? And then 3, you test inputs in each interval. So I'm going over this because we definitely struggle with this a little bit. So the first part we already did. We saw that f prime was 0 when x was plus or minus 1, and f prime doesn't exist when f equals 0. When x equals 0. So the part where we struggled here a little bit is that once we find that, we first have to remember that as well, we have to include places where the function doesn't exist. If you want to find when a function is positive or negative, find where it's equal to 0 and where it doesn't exist. The thing to remember afterwards is the number line, you divide it with places, with inputs of not only where your function equals 0, but also where it doesn't exist. And in that first homework and in other homeworks, this is the part where we usually messed up. We were good in dividing the intervals where places where the derivative equals 0, but we forgot that we also had to include the place where the derivative doesn't exist. And the same is going to happen with the second derivative. Because for concavity, what are you going to do? You're going to check where the second derivative is positive or negative. So it's going to be the same process. So for concavity, you're basically going to replace here f prime with f double prime. You're going to check where f double prime equals 0 or doesn't exist. And when you go to the number line, you're going to divide the number line where places where the second derivative equals 0 and also where it doesn't exist. So never forget, you also have to worry about where the function doesn't exist. Right? That's the part we're forgetting. And again, I'm stressing this so you don't forget it. Right? And then step 3, so let me do step 3 here. Step 3 was just testing values in each interval. It didn't really matter what value you chose. Right here, you could choose -2, -1/2, 1/2. So just pick simple values in 2. And then you would plug them into your derivative, right? Whatever function it is you're working with. So you check the sign of that, the sign of that, the sign of this, and the sign of this. And then actually we can go ahead and do this real quick because it'll be a good summary as well of how to find local maximums and minimums. So let me put it into my calculator. So let me write my derivative. So derivative was x squared minus 1 divided by x squared. Then when I evaluate these values, so f prime of -2, that's positive. I get 3/4, so that's positive. Positive. F prime of -1/2. Get -3, so that's negative. So remember, for things like this, all that matters is whether your function is positive or negative. In this case, the derivative. So you don't actually have to find the exact value. For f prime of 1/2, I get -3. So I get negative again. And then for f prime of 2, I get 3/4, so I get positive. So I'm negative on this, positive on this interval, negative in this interval, negative in this interval, positive on this interval. Right? So then you can just read off your answer. Okay? So it implies f is increasing wherever the first derivative is positive. So that's the intervals -infinity to -2, union 2 to infinity. Oops. Oh, sorry. Yeah, see, I always do this mistake. Right, so remember to use the actual interval values, not the values you tested. So this is -infinity to -1, union 1 to infinity, and decreasing, well, wherever the first derivative is negative. So this was the interval -1 to 1. It was the first derivative was negative there. So -1 to 0, union 0 to 1. And then remember, since the derivative is 0 at 0, we have to always separate that interval. Right? So I said -1 to 1, but really you want to write it as -1 to 0, union 0 to 1. Now we can also read off local maximums and minimums here, because this is basically the same process you're going to do to find local maximums and minimums. Right? You do this whole thing, find where the derivative equals 0, where it doesn't exist, plot it on a number line, test values in each interval, and then wherever your derivative changes, the sign of your first derivative changes sign, that's going to be a local max or local minimum. For example, to the left of -1, we're positive. To the right, we're negative. So you want to think of something like your function was increasing, then decreasing. So x equals -1 is a local maximum. And again, that's how I remember it. I don't actually memorize, okay, if it goes from positive to negative, the first derivative, then it's a local maximum. No, I just draw a picture. Okay, increasing looks like this, then decreasing. Oh, okay, the shape looks like a local max. Now from on the left of 0 and to the right, we're negative, so there's no change there. Then at x equals 1, to the left we're negative and to the right we're positive. So what was going on? We were decreasing and then increasing. Oh, so you see, okay, that's a local minimum. So we're basically killing a bunch of birds with this example. So just by doing this, this setup that I did, right, finding where the derivative equals 0 doesn't exist, drawing the number line, testing values in each subinterval, you do that to find where the function is increasing or decreasing. In turn, you use that information to find local maximums and local minimums. Now for concavity, so for find where the function is concave up or concave down, you do the exact same thing. So for concavity, and don't start a sentence with so, sorry. So for concavity, do the same process. Instead, your function is going to be now the second derivative instead of the first one, which implies the first thing was find where now not f prime, but f double prime equals 0 or doesn't exist. And it's the same thing. Just change the function to f double prime. Divide the number line with these values. And then test intervals. Okay, so it's the exact same process. The only thing is that your function now is the second derivative for concavity. And it's the exact same process because for concavity, you're looking for what are you answering? Well, concave up is when your second derivative is greater than 0. Concave down is when your second derivative is less than 0. So you do the same process instead with your second derivative. And you find inflection points the same way. Wherever your second derivative changes sign, you get an inflection point. And so it's kind of similar to finding local max and minimums. So wherever the second derivative, wherever f double prime changes sign, that's an inflection point. And here there's no difference. There's no local max or minimum. It's just an inflection point. So for sake of time and for sake of keeping this video short, and because we already did the exact same work just for the derivative, I'm just going to leave it at this. The work is the exact same work we did in the previous part. Right? So all this work we did here, the only thing is that you change f prime with f double prime. Okay. And again, we did examples of that as well in either section 4.2 or 4.3. Yeah, so 4.2. Now, constraint optimization. Right? This was something that was kind of similar to related rates in the sense of how we approach the problems. Right? And here you get a little bit of the hints that I gave you when you do something like this. So you want to identify the function you're trying to maximize or minimize, whatever constraints you have, and then usually you're going to look for either absolute maximums or minimums or local maximums or minimums. So let's see if there's an example of this in the study guide. So L'Hopital's, this mean value theorem. So that's in the homework. I'm still going to talk about it a little bit. Linear approximation, I do want to talk about. Yeah, okay. So it's an example of optimization problem. So how do I know it's an optimization problem? Well, I said there's a function there. And what is the problem asking? Well, you want to maximize this function, right? Because this function is giving you distance, right? So that's an optimization problem. You're trying to maximize or minimize something. So see how this works, right? So problem 6 in the practice exam from spring 2019. So tests show that if a car is driven at a constant speed of x miles per hour, it can be expected to travel a distance of f of x equals a times x divided by c squared plus x squared miles before engines fail. Here, a and c are positive constants, right? So a and c are just numbers. We don't know what they are, but there's some numbers. So at what speed should the car be driven in order to maximize the distance a car can travel during its lifetime? Right? So what do we do here? So the steps are, so an extra step. So first, let me write bonus step. So sometimes you want to draw a picture if it actually helps. In this case, I don't think it doesn't. So I did an example in my notes, in my videos for section 4.4. I think you should go back because those are good examples. I think I did 3 or 4 examples, which was just examples like this. Definitely go look on that section in the videos. So all I did was examples, and in some of them I had to draw pictures, like the one where I had a fence. I wanted to maximize the area of a fence or something like that. And there you wanted to draw a picture just to see so you had everything right. So let's draw a picture if it helps. So let's say, for example, this is a fence. So this is the area of the fence. So I want to maximize the area of the fence. So what do we do here? So 2, or let's just say 1, find the function you want to maximize, or the expression. You want to maximize or minimize, in this case, maximize. 2, and I might have done these in a separate order in my notes, but 2, you want to find constraints on the variables. And then 3, write an equation that relates write an expression or function that relates your variables, which we already have. Right? We're given what f of x is, so we don't really have to do it, but I'm going to write it. So find any expressions that relate variables, because if you remember from the videos we did in class, we usually ended up with a function. So the objective function that we wanted to maximize or minimize, it was usually a function of 2 variables, which we don't know how to differentiate. So what we did is we used the constraint to solve for it. So find any expressions that relate variables. So here, I'm not going to do the whole problem. Let's just do it real quick. So like I said, we don't need to draw a picture. So no bonus part. Step 1, the objective function was given to us. So what's it? Ax divided by c squared plus x squared. Okay, so it was given to us. Any constraints? Well, we do have some constraints. What do we have? Well, a and c have to be positive. So a and c greater than 0 are constraints. What else? Speed, right? Can our car ever have negative speed? No, right? Because speed is the absolute value of velocity, right? So speed is always non-negative. So it's either 0 or positive, right? So x has to be either 0 or positive. So what are our constraints? As we saw, a has to be positive, c is positive, and x can be 0 if the car is not moving, right? Obviously, then the speed is 0, or positive, right? If it's moving. And then how do you solve this? You want to maximize or minimize. Well, you can check what the domain is, because we talked about an algorithm to do things like this. So here you can remember, so in step 3, when you're taking derivatives, you want to remember that if the function is continuous on a closed interval, just look for absolute maximums and minimums. And then how do you find them? You test the critical points in the function, test the endpoints of your interval in the function. Whatever's the largest value is your absolute max, whatever's your smallest value is your absolute minimum. So we did that before. Right? So there's either 2 cases. Either you are in a closed interval or you're not. In this case, our domain is not a closed interval, right? Because what's the domain here? Well, we have our function. That function exists everywhere, right? Because the denominator is never going to be equal to 0, because x squared is a positive number. C is, or 0. C is always positive, so you add a positive number plus something that's 0 or positive, it's always positive. So the denominator is never 0. So this exists everywhere for x, but we also have the constraint that x is greater than or equal to 0. So the domain is 0 to infinity. So again, like I said, 2 cases. Either your domain is a closed interval and your function is continuous there, or it's not. Whenever it's not a closed interval, then you're just going to look for local maximums or minimums. Okay, so those are the 2 things you want to keep in mind. If it's on a closed interval and continuous, look for absolute maximums and minimums. If it's not a closed interval or it's not continuous in a closed interval, look for local maximum or minimum. And that we know how to do, right? Take the derivative, set it equal to 0, or find where it doesn't exist, do the number line. We did all that a couple minutes ago. Okay. That's basically all that happens here. Again, if you have 2 variables, you're going to want to use one of the constraints to eliminate one of the variables. Okay. An example of that was, and again, I did this example in a video. Basically, your objective function was a squared plus b squared. And then one of the constraints, so just one, not all of them, I think the constraints were a is greater than 0 or equal to 0, and you have another constraint, a plus b equals like 13. You would use this expression here to write your objective function as a function of one variable. Right? That's the only other thing to remember. Okay. Again, I did this in section 4.4. I did 3 examples. They include all of these. Please look all of it, section 4.4 videos. Okay. So sketch a graph. That was section, let's see, so section 4.3. I don't know if it was my section 4.3, but basically all I did for that was my video was just, okay, here's a function. I'm going to get the information from the function, information from the derivative, information from the second derivative. So I'm pretty sure that was section 4.3. So just go ahead, look over those videos, over that video, section 4.3, and you should see everything you need there. So this, it's not going to be hard. It's going to be hard in the sense that you have to get all this information, but we already know how to do it. Right? Because you know how to get all this information from the previous part. You saw how to do that. Then it's just graphing a function using that information. So that might take a little bit, but since you already have all the information you need, you should always get it right. It might just take a little bit of time to do it. Okay, so that's that part. Okay, so average slope, right? Remember, that's just the slope of the secant line. So average slope, that's the formula, f of b minus f of a, or b minus a. Nothing crazy there. Now, determine whether the mean value theorem applies. That's important. What are the conditions for the mean value theorem? You have to check 2 things. And I asked this in the homework that was due this Friday, last Friday. Now it's due this Saturday, right? And some people wrote it, most people didn't. So this is important. So conditions for mean value theorem to apply. On an interval AB. Basically, have to check 2 conditions. First, your function f has to be continuous on that interval. The second part is f prime has to exist on the open interval. Remember, derivatives only work on open intervals. Okay? So then, you only have to check those 2 things. Most people were okay with checking that the function was continuous, but for some reason they struggled with whether the derivative existed. Remember, how do you test if a derivative exists? If you can find the derivative, it exists. It's as simple as that. So the example in the homework, I don't know if it was this exact same one, but it was something like f of x equals 4 sine of 2x on, let's say the interval was negative pi to pi. So this wasn't the exact same thing, but it's going to be the same process. And you want to ask, does the mean value theorem apply? Well, we check a couple of things. So first, you can say, okay, is this function continuous? 4 sine of 4x is a composition. So this is one way to do it. I think the easiest one, the algebraic way to do it, is a composition of 4 sine of x and 4x, right? You're plugging, and 2x, you're plugging 2x inside 4x. The composition of 2 continuous functions is continuous. Another way you could explain this is, well, we know sine is continuous. Multiplying by 4 on the outside is a vertical stretch or compression. Multiplying by 2 on the inside is a horizontal stretch or compression. Those don't change the continuity, right? The function, you can still draw the function without lifting your pencil. It's just stretch or compressed, but it's still continuous. So that's the other explanation. I think students said that they were more comfortable with the algebraic, which is this. You have a composition of continuous functions. It's if they're both continuous, the composition is continuous. Or use graph transformations. Okay. So I think most people were okay with this. Now for the second part, does f prime exist on AB? In this case, negative pi to pi. Well, it's simple. Just find the derivative. If you can find it, it exists. Well, so f of x was 4 sine 2x. What's the derivative? Well, this is by the chain rule. It's negative 8 cosine 2x. Oh, the derivative exists. I can find it. It exists everywhere, right? So it exists on the interval negative pi to pi. Right? So if the derivative exists on your interval, it's differentiable. That's what differentiable means. The derivative exists. So please remember that. And then what's the conclusion of the mean value theorem? Well, there exists a C such that f prime of C equals the slope of the secant line between the endpoints. So here f of pi minus f of negative pi divided by pi minus negative pi. People here were able to do this right? This is just read the theorem. And then you could solve for C, right? Plug in what this is, plug in what this is, and solve for C if it asks for that. So that part wasn't hard. Again, the part where people really struggled is the function differentiable. But please, if you get a question about whether a function is differentiable, find the derivative. If the derivative exists on that interval, that's what it means for a function to be differentiable. The derivative exists. Okay. So that takes care of all this part. Now, L'Hopital's rule, people did pretty okay. For the most part, I'll see. I have like 2-3 minutes left, just 5 minutes left. Let me go over the problem about approximation because I didn't ask about it in the homework. So approximation is very straightforward, linear approximation. Yeah, so approximation, super straightforward. What's the idea about approximation? The main idea is you can approximate f of x near x equals, let's say, a, using the linearization, basically using the tangent line, going through x equals a. That's it. So let's see what it says here. Differentiable function f satisfying f of 1 equals 3 and f prime of 1 equals 2 is approximated by linearization. Remember, the linearization, this L of x is just a tangent line at x equals a. In this case, your x is your input, so it's your x equals 1. Just remembering that L of x is the tangent line. We already know how to find the equation for the tangent line. So explicitly determine the linear function L of x. It's a tangent line. We know how to do it. Right? So L of x at x equals 1, right? So the tangent line at x equals 1, well, we know its slope. That's the derivative of x equals 1, which we're given. And we know a point going through it. Right? Remember, to find the equation of the tangent line, all you need is a slope and a point. The point is, well, the point on the function. The input is 1, the output is 3, so the point is 1 f of 1 or 1 comma 3. And then just use the point, the slope intercept? Yeah, the point slope formula, right? Do y minus the y value equals m, x minus the x value. In this case, we get y minus 3 equals 2, x minus 1, and simplify. So if I simplify this, I get negative 2 plus 3 is 1. So this is 2x plus 1. And this is the linearization. It's just a tangent line. Very easy to find. Now, what do you do? For x values close to 1, you can approximate the function. So instead of finding, and this is what this is asking, instead of finding f of 3, use the linearization. find L of 3, because this is an approximation. So you just basically plug 3 into your tangent line, and that's it. That's the approximation. That's how you're approximating f of 3. You're using the linear approximation, which is the equation for the tangent line. Is it possible for the estimation in B to be exact? That's a good question. It is possible. So when is it possible? It is possible if your function is a line. Right? Because if your function is a line, what's the linearization? Well, the linearization is going to be the same line. So this could be exact. So of course, if it is, this is one case where it's possible. If it is a line, if f is a line, if the original function is a line, this is certain. This is definitely exact. Okay. Now, is it possible for the estimate in B to be off by more than 10? Yeah, it's definitely possible, right? Because we're pretty far off from 1, and we're doing this at x equals 1. If you remember the examples in class, if we're using the linearization at x equals 1, usually we were approximating L of L of 1.1, something really close to 1. Here, our function could look something like this, okay? So our function looks like this here. This is x equals 1. So that's f. This is the line. This is L of x. And then our function, well, the function could go there, like be crazy, right? So our linear approximation will look nothing like this. And let's say maybe this is x equals 10. Yeah, so it's definitely possible. It's just an approximation. The further away you are from the x value where you're approximating, the more likely that your approximation is going to be bad. Now, I'm done. I'm done with time. I can't do any more. L'Hopital's rule, I think you guys are doing pretty good. You can just go ahead and watch the videos. Ask me any questions about it. That's section 4.7. The last thing I want to say about linear approximations. So last thing about linear approximations, which they didn't ask in the spring exam, but they might ask in the actual exam for this spring. Well, we already know that we can approximate. Right, so we can approximate f with the linearization. We just find the equation of the tangent line. The other thing is we can approximate the change in f, which I think in my notes I wrote as the change in y. We can approximate it with the change in the linearization, which we had an exact formula. This was f prime of x times change in x. Where x here, let's say x naught, this was the place where you found the tangent line. Right, so this was the base. So x value, it could be a couple things for you to recognize it. X value where you found the tangent line, or the linearization is the same thing. It could be the x value that doesn't change. Right? And what do I mean by that? In the examples I did in my notes, you were given usually something like x changes from x equals 1 to x equals 1.1. So what would that mean for us? X naught would be 1. The change in x would be, well, how much does x change by? 1.1 minus 1, which would be 0.1. And of course, you would have to be given the derivative at x equals 1, or you would have to find it and evaluate it. And then you just plug things in. So this is the other thing. You can approximate the change in the function by, of course, doing change in the linearization, and it's just this formula here. Just find the change in x and find f prime of x naught. Right? We did an example of that in the notes. And again, that's all the time I have. L'Hopital's rule, I did a couple videos about this, section 4.7. Go watch over the videos. Any example you're gonna get are gonna be like something I did in my video, so please watch over them. If you have any questions, please let me know.